we're going to take a look at a few more examples of using the transformation theorem. We're going to do one more rotation, but in this case, we're going to look at R3 and performing a 90-degree radian, or 90-degree theta, so we shouldn't say radian, excuse me, rotation around the z-axis in the clockwise direction. Okay, so let's set this up. I'm going to draw kind of a 3D representation of this. So I'll label these x, y, and z. And it shouldn't matter, I mean, other than z-axis having to be the vertical, that's the only important part. Now the vector 1, 0, 0, if we imagine where that would be. Oh, and we should probably start off stating our definitions. So our transformation is going to take a vector that is in R3, and we're going to produce another vector that is in R3. That's just a 90-degree rotation about the z-axis. Then in this case, because we are in R3, we'll have 3 standard basis vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so to conduct this transformation of, first of all, the 1, 0, 0 vector, we have to ask ourselves, what would be a 90-degree rotation in the clockwise direction? Okay, so clockwise, imagine that we're looking down this way, right? And so what do we see? Well, let's pretend like we take this axis and just rotate it around like this. So here's our z-axis. Here's our z-axis we're staring down at. So clockwise would go this way, meaning clockwise would be in this direction. And so it would rotate from a position of 1, 0, 0. So be on the x-axis, and if we rotated it 90 degrees, then it would be on the y-axis, and it would go from being 1, 0, 0 to being 0, 1, 0. So it basically just changes directions into the y-axis. Now for the other one, E2, the second standard basis vector in R3, we again ask ourselves what's going to happen to that guy. And it's just so I don't have to draw this picture over and over again, I'm just going to say, all right, well that is the vector 0, 1, 0, this green vector, and that's going to rotate 90 degrees this way, 90 degrees that way, which will put it back on the x-axis, right? So imagine what we're saying here is we're saying, here's the vector 0, 1, 0, and if you rotate it clockwise, it will be pointing this way, so it'll be back on the x-axis, but because x is positive here and negative here, now we have a position of negative 1, 0, 0. So that vector becomes negative 1, 0, 0. Finally, to do E3, that's going to be a vector that starts off on the z-axis. And if you think about it, if you rotate something that is standing up and you rotate it vertically, it's not going to do much rotation because it's already on the axis itself. So here's the vector 0, 0, 1, and if you rotate that about the z-axis, well, it is on the z-axis, so it's kind of like just taking something and just twisting it around in circles, right? You're rotating it, but it's not changing the fact that it's pointing straight up. So this will still be the vector 0, 0, 1. And so what we know from the transformation theorem is to form the A matrix, we have to take as the first column the transformation of E1, which was the vector 0, 1, 0. As our second column, it'll be the transformation of 0, 1, 0, which became negative 1, 0, 0. And the third vector, which was 0, 0, 1, remained the vector 0, 0, 1. And so there is our transformation matrix. And so if we feed this guy any vector, then it should rotate it 90 degrees. Let's think of one that it makes sense in this context, that we could actually visualize. Perhaps let's look at what happens with 1, 1, 1. If we take 1, 1, 1, and we're kind of just doing a check here to see if what we get makes sense. Negative 1, 0, 0, 0, 0, 1. Now remember the z component, not going to change, right? Because that guy is a 1, and it's going to remain a 1. So we should see that as well. And if we add 1 times this column plus 1 times this column plus 1 times that, we get negative 1, 1, 1. So if we imagine what happened here to this vector, we started off with 1, 1, 1, which is 1 unit this way, 1 unit this way, 1 unit this way. So I'll kind of draw it like this. Now remember, 1 unit up is actually the same height as this, but because it's closer to us, it's going to look lower in the plane. So there's 1, 1, 1. And then negative 1, 1, 1, if this is x, then that is going to put it basically over here at the position, the same height, but negative 1, 1, 1 would be right there. So although I didn't do this very much justice in terms of drawing it, notice that it did rotate at 90 degrees. That in other words, this sweep right here, that would be a 90 degree angle. So the angle between these guys is 90 degrees. One way we could just verify it to see if what we got makes any sense at all. All right, well, there are many other transformations. We don't have to physically be doing something in geometry. We could just be manipulating data. So anytime you've computed a mean, a median, or a mode, taking a bunch of data and you're compressing it down into a summary value, or standard deviation, or range, any measure of the spread of how spread out data is. So sometimes we're just looking to manipulate data. And so we might have situations where we're taking something in one dimension, say a 3x1 vector, and we want a 1x1 output. And what we want to do with that 3x1 vector is we want to represent the average of the 3 components. So, okay, here we are going from, in this transformation, we're going from R3 into R1. Okay, R3 is 3 dimensions, R1 is just the number line. It's just one axis. And so if we are in R3, we have those 3 same standard basis vectors, which we will write down as 1, 0, 0, 0, 1, 0, and 0, 0, 1. That vector, now we have to think about what these become under the transformation. If you transform E1, what are you doing to it? Well, you're producing the average of the 3 components. So the average of 1, 0, 0 would be 1 plus 0 over 3, which is 1/3. Now, to do E2, believe it or not, it's still going to be the same answer. It's just going to be 0 plus 1 plus 0 over 3, which also gives us 1/3. And finally, transformation of E3 gives us 0 plus 1 over 3, which once again is 1/3. To form the A matrix, remember what we do is we place the transformed values in as the columns. In this case, each column is just going to contain one value, and it's going to be the 1/3. And so notice that this vector, this matrix, is a 1/3. So if you take a 3x1 vector, any 3x1 vector, let's just do it as a test. Let's say we took 1/3, 1/3, 1/3, and we multiplied it by 3x1 vector, we'll say 3, 4, 5. Okay, well the average of 3 plus 4 plus 5 divided by 3 is 4. And look what happens here when we multiply these. We take 3 times 1/3, plus 4 times 1/3, plus 5 times 1/3. And that's the same thing as 3 plus 4 plus 5 all over 3 by common denominators, 3 over 3 plus 4 over 3 plus 5 over 3, which gives us exactly 4. And that checks out. That's what we wanted. Okay, 2 more short examples. Now in this case, notice that we're instead of being verbally described what we're doing, we're looking at this symbolically. So if I read this transformation takes in a vector, 2 components, and we'll label those components A and B. What comes out in the top component, this output vector will report the difference between B and A. And then it will also report in its bottom component twice the value of A plus 3 times the value of B. So all I have to worry about is what is this transformation dimensionally doing? Oh, and by the way, up here, notice that we had m by n was 1/3. So that described our matrix. We didn't need to worry about the dimension of that because as long as we transformed each of the vectors, that did all of the work for us. So here we're taking an R2 vector, making an R2 vector out of it. So A should be a 2 by 2, m by n. Remember, this is n is 2. Over here we have m is 2. And the basis vectors in 2 dimensions we know are 1, 0, and 0, 1. So to transform the 1, 0 vector, we need to do the following. In the top component, so this guy is what we're calling A, and this is what we're referring to as B. So B minus A would be 0 minus 1, which is negative 1. And in the bottom component, we'd have 2 times A plus 3 times B. So that would be negative 1, 2. That would be the output vector. So that vector, this transformation, all it does is it takes the input vector, takes the bottom component minus the top component, puts it in the top component. Takes twice the top component plus 3 times the bottom component and drops it in the bottom. Now for the final one, 0, 1, this is going to take, again, B minus A, so 1 minus 0, and 2 times A plus 3 times B will give us 1, 3. And so now to construct that A matrix, well, we've been doing this a number of times here, so negative 1, 2 is going to go in the top, and in the bottom, in the leftmost, the rightmost will be the vector 1, 3. So now if you multiply this by anything, by any vector, it should do exactly what this describes. Let's take a look at a quick example. Let's do a quick test. I'll just pick a vector, negative 1, 2, 1, 3. We'll say 4, 3. 4, negative 3. How about that? So if we take 4 times negative 1 plus negative 3 times 1 will give us negative 7. And if we take 4 times 2 is 8, minus 9 is negative 1. So let's see, did it do it? B minus A, negative 3 minus 4 is negative 7. 2 times 4 is 8, plus 3 times negative 3 is 8 minus 9, which is negative 1. This checks out. Final example. Here we are going, notice, from a vector that is in 4 dimensions. It has 4 components, 1, 2, 3, 4, w, x, y, z. And we're going to output a vector that is in R2. Okay, so that means that the A matrix that I expect to get here, so here, notice we did get a 2 by 2. I expect to get a 2 by 4 because n is 4, m is 2, and this should be m by n. So, what are the R4 vectors? Well, there's kind of a number of them, right? E1 through E4. E2 would be 0, 1, 0, 0. E3 would be 0, 0, 1, 0. And E4 would be 0, 0, 0, 1. All right, let's transform each of these. Okay, so to transform E1, what do we need to do? Well, in the top component, we're going to take 2 times the x. So here, notice this is our w, x, y, and z. And that's just how we have them labeled. They don't have to be called w, x, y, and z. It just tells us that the top component will be 2 times the x, 3 times the y, minus 1 times the z. So let's see if I can do this. 2 times 0 is 0, plus 3 times 0 is still 0. So I'll just write this first one out. 2 times 0 plus 3 times 0 minus 0. Well, that's just going to be 0. Bottom component is going to have the x plus the y plus 3 times the w. So x plus the y plus 3 times the w, which is 1. And that's going to give me 0, 3. That's the vector. Transformation of E2. I'll just kind of do this in my head now. So 2 times the x, which would be 2, plus 3 times 0 minus 0 is just 2. And then the x plus the y plus 3 times the w will just be 1 plus 0 plus 0, which is 1. That gives me the vector 2, 1. E3, 2x plus 3y. So really all I have to worry about is where the 1 is, and that's in the y position. 3 times 1 is 3. And then x plus y will be 0 plus 1 plus 0, which is 1. And lastly, we have the transformation of E4, which, again, is just going to depend on the z component, so it's going to be a -1 in the top, and then it's going to be all zeros. X, Y, and W are all zeros. So our A matrix would be 0, 3, 2, 1, 3, 1, -1, 0. And there it is. And if you notice, look at where the coefficients are: 2, 3, -1, X, Y, Z. 3, 1, 1, W, X, Y. Pretty cool little tidbit there.